Hello all, today we're going to be working on 7.2, which is some special exponential equations. I want to do a quick preview. We're going to talk about half-life, which means we are going to have the initial value of some amount over time periods, determined by the time period I should say. Our second one is going to be this financial formula, which is compound interest. This is one of the most important financial formulas that you can utilize. Deals with principal, how much you start with. You have the rate, typically an annual interest rate, the number of times a year it's compounded, then that's raised to the interest compounded multiplied by the time in years. That's going to be really, really important. And our last function is going to be the continuously compounded function. And you're going to see that this is going to be PERT. We call that PERT because we take the principal times the natural number e raised to the RT power, which is interest rate times time. We do not change the interest rate. It'll be in a decimal form. We don't add 1 to it or anything like that. So let's take a look. Let's go back to our original, which is going to be half-life. Again, half-life is going to be the amount of time required for the amount of something to fall to half of its initial value. Again, the initial value is A. We're going to have time in years, and that's going to be cut into half-lives, so however many days that we have. So in example 1, we have an A value. So we have a hospital prepares 100 milligram supply of technetium 99M, which has a half-life of 6 hours. So I'm going to underline some or highlight some important things. We have 100 milligrams, that's our A value. It has a half-life of 6 hours. So the half-life formula doesn't really change. It's an exponential decay. We cut our values in half, so we're going to use a half in every single one of these. So the exponential decay for this supply will be y is equal to 100 milligrams times 1/2 raised to the t divided by 6, because it happens in 6 hours. Now this time, the time is always in hours. So we have to be very specific what we have. So on part B, it says use the function that we created to determine how much T99M is left after 3 days. Well, first and foremost, 3 days is really going to be 72 hours. So that's our first component. So I'm going to plug it in. Y is equal to 100 times 1/2 raised to the 72 over 6 power. And so this is all calculator work. 100 times 1 divided by 2 raised to the power of 72 divided by 6. And we get this answer right here, which is going to get us 0.024414, all that other good jazz. But this is how much we have left in milligrams. Because we started off with milligrams, this is what we end up with. This is very important for medication. We have to know how much is left in the body after a certain amount of time so we can prescribe these to people. We're going to switch it up to phosphorus 32. This has a half-life of 14.3 days. So that's important. We need to write the exponential decay function for a 50 milligram sample, and we want to know how much is going to be remaining after 84 days. So we're stuck into days for our time. That's really, really important. But we have y is equal to our sample, which is 50, times a half-life. We're going to cut the sample in half for every time period of 84 days divided by 14.3. Again, this is just a calculator problem. We're going to put in the calculator 50, parentheses, 1 divided by 2, raised to the power of 84 divided by 14.3. If you hear me clicking on this side, I'm actually calculating these with you guys. So this is what it looks like. It looks like 0.85247. So 247. Now I would just keep it to the hundredths. So I'd have this, and this is going to be in milligrams. So after 84 days, with a half-life of 14 days, we only have 0.85 milligrams of this phosphorus 32 left in whatever system. So we use half-life for a lot of things, typically really useful in science, radioactivity, and other types of sciences really use half-life quite a bit, exponential decays. So this time we're going to switch gears. We're going to do finance, and we have 5 values that we need to know. We have A, P, R, N, and T. A stands for our our final amount or our appreciated amount. We have a P value, which is standing for principal, how much we start off with. We have R, which is going to be our rate, so whatever our interest rate is. This is going to be really important. We need to change all of our percentages back into decimals. And then we have our N value. N is going to be really, really particular here. N is very, very special because N tells us how many times we're going to compound this. So you can see that it happens, we divide our rate by it first and foremost, and we raise it to the power of N times T. T is going to stand for time, and typically time is always going to be in years unless it specifies otherwise. Don't plan for it to specify otherwise. Okay, so I'm going to utilize this equation for yearly, and then quarterly, and monthly, and daily. And so I'm going to write these equations out. So our example says $50,000 is put into a savings account that pays an annual interest rate, of 2.5. I'm going to change this right now to 0.025. 0.025, because that is actually 2.5% written as a decimal. We need to always convert our percentages into decimals. If you need to know how to do that, you start off and you move it left twice, our decimal from the percentage decimal. So I want to calculate the amount in the account after 4 years if it is compounded yearly, quarterly, monthly, weekly, daily. So the number of periods it's compounded in a year is 1. If we compound it quarterly, it's 4 quarters in a year. Monthly is 12. There are 52 weeks in a year, and there are 365.25 days, if you really want to think about it, daily. The compound interest formula is going to be the same for all of these, but we are going to change our N values. So A equals, in this case, 50,000 times 1 plus 0.025 divided by 1 raised to the 1 times 4 power. Now, the reason why it's 4 is because it's going to be the amount after 4 years. I can change this to a T, but I'm going to keep it as 4 so you can see what I'm going to put in my calculator. The same formula here, 5,000 times 1 plus 0.025, but this time it's divided by 4 since it's quarters, and it's raised to the 4 times 4 power. Same thing here, 5,000 times 1 plus 0.025, this time divided by 12, raised to the 12 times 4 power. Now I'm just going to keep on writing things out, as you should do as well. We're really not changing anything, we're just changing the time periods, so the N, and it's really nothing special. This is very useful for financial math. We use this for all different kinds of rates. So make sure that this one lives in your long-term memory. I will tell you that it's very rare to find anything more than yearly for, say, stocks or dividends. Sometimes dividends will happen, but that's not really compounded. It's just quarterly or semi-annually, things like that. If you're lucky, you'll find some things that will happen semi-yearly, but it's not typical. Typically, maybe municipal bonds. But anyways, I'm going to plug these in the calculator, and I'm just going to change some values around. So I have 5,000 times parentheses 1 plus 0.025 divided by 1 raised to the 4th power. So on this one here, on my first one, I end up with $5,519, and it looks like 6 cents after 4 years of accruing interest, which is not bad. It's not great. It's not as good as the stock market average, but we're doing okay. I'm going to go into my calculations and change it a little bit, change it to the next one, which is dividing the rate by 4 and raising it to the 16 power instead. And I get $5,524.14 rounded up. Same thing, I'm going to have to now change this to 12. So 12 and then raise it to the 48th power. Wow, that's going to be a lot. Okay, so it looks like in my formula I get $5,525.28. Same thing. I'm really just plugging in the calculator off screen so you guys don't have to worry. I'm not doing anything weird on the calculator. It's literally just what you see. This time I'm going to raise it to the power of 52 times 4 for my next one. And the values are increasing, but they're getting very small. You might say that they actually have a diminishing returns here. And we're not really doing anything special with the formula. I'm literally plugging in the same formula and just modifying small numbers here. So I'm not doing anything special. 365 times 4. My last one here is 55,025 and 83 cents. And you can see that the gain between the first two is actually quite large, and then it gets smaller and smaller over time, so smaller gaps. And that's because this is an exponential growth formula, but it's only happening within a certain time span, so you're really just smoothing out a curve, essentially. You're getting closer to a continuously compounded curve. And we'll talk about that in just a bit. But so what I want you to see here is that if we keep on compounding it more and more and more, we will reach a threshold, and there will be diminishing returns, but the more that you compound, the more money you make. So that's what you're hoping for when it comes to the stock market, or higher interest rate. That's really what you're looking for. So number 3, we open a savings account and we earn 2.12% interest rate. Now I am going to change this immediately to a decimal, so this is 0.0212 interest compounded quarterly, so that's 4, n equals 4. And you began with $2,500, this is our principal, and then we want to know how much we'll have after 2 years, so this is our t value. So in a calculator, I'm just going to plug in all my things, so $2,500 or $2,500 times 1 plus 0.0212 divided by 4 and raised to the 4 times 2, which is 8. And so my end result is 2,500 times 1 plus 0.0212 divided by 4 raised to the 8th power. We end up here with $2,607.99 rounded. That's how much we'll earn after 2 years. I don't think that this is a great investment, but it shows you how to use the formula. All right, we're going to talk about compounding continuously. So this time we're going to start off with $1. So this is our P value, our principal. We have an interest rate of 1, so this is 100%, so that's 1 as a number. And we're going to calculate the amount in the account given that it's compounded 1,000 times, 10,000 times, 100,000 times, and 1,000,000 times. And so you're going to see what happens here is we start off with $1. We multiply it by 1 plus 1 divided by 1,000 raised to the 1,000 power, because we're only going to calculate this for 1 year. That is our time. So it's just 1,000 times t, or times 1. This is going to be funny because you're going to notice the numbers that happen here are not crazy, but definitely a little awkward when you see the pattern. So raised to the 1,000, here we go. My first one is 2.716923932. And it says evaluate to 9 decimal places, so I'm just essentially going till the calculator stops. Now this probably doesn't mean that it ends. Maybe it's keeps on going on for a while. This one might have a pattern. Let's see the next one. I'm going to add in a 0, insert a 0 here, do the same thing for the power. I'm talking to myself, but so I'm going to do the same formula, 1 times 1 plus 1 divided by 10,000 now, all raised to the 10,000 power, and I get 2.718145927. Again, following the directions. So I'm going to do the same thing, but I'm going to add another 0. So my formula that I put into the calculator is 1 times 1 plus 1 over 100,000 raised to the 100,000 power, and I got 2.718268237. Okay, and I'm going to highlight what you guys can see that are going to be very similar. So last one, 1 times 1 plus 1 over 1,000,000 raised to the 1,000,000th power. It's a lot of zeros. And and I get 2.718280469. What we're really doing here is we're getting to this continually compounded number, and it's a pattern. And it's represented by E. So if you hit the second button on most of your calculators and you hit ln, or natural log, and you put in 1, e to the first power, you get this number of 2.718281828, and it keeps on going on forever and ever and ever. It's an irrational number, just like pi is. And we call it the natural number E. And we use it for this formula here, PERT. Does not hurt to remember PERT. So in this case, we have a final amount, which is A, is equal to our principal, times the natural number E, this is our base, raised to the rate, times time. So it's still pretty similar to what we've been doing, but all we're doing here is we're looking for a continuous curve that we would try to get towards when we are investing our money. This is what we'd call an unachievable goal in financial math. We want to get to this continuously compounded interest, but we are only going to be able to do it in steps and stages. So A in this situation is equal to, let's see, we open a savings account with an interest rate of 2.12%. So here we go. I'm going to change this automatically to 0.212, 0.0212, there it is. And it's compounded continuously. This tells me my base is E. If we began with the same principal, $2,500, well, how much will we have after 2 years? And you're going to notice we're going to be very, very close to what we started with. So, or with our previous example, 2,500 times E raised to the 0.0212 times 2. And so I'm going to plug this in my calculator. 2,500 times e to the 0.0212 times 2. And remember in here, it has to be 0.02 because it's 2%. And so what this is approximately equal to is $2,608.28. So I'm going to scroll up, and we're going to compare it. So this one is 2,608. That is the hopefully achievable. But you notice when we compounded continuously quarterly, it was less. This compounded continuously happens every second of every day. It's really not feasible. So it makes a very, very smooth line on a graph. It's just what we try to attain, though it will never be attainable. So these are the notes for chapter 7.2. And we have homework on pages 8 and 9. If you run into any snags, make sure you watch this video a few times. Not many of these problems are going to show up in your real life unless they are going to be compound interest. HalfLife you'll see when you're doing science and chemistry and other things talking about radioactivity. But compound interest happens all the time, and it's a very important formula for you to memorize. So I hope this lesson was good for you guys. If you have any questions, please feel free to reach out to either me or one of my colleagues. Have a great day.